Be sure you write down this essential question. It showed up gray on those notes that you picked up on the stool. Showed up really gray. But what we're going to concentrate at first is how we can quickly graph exponential growth and decay functions. Yesterday was a review on, or I shouldn't say review. Yesterday was exposure. How will functions look different in their equations, their tables, their graph? And we concentrated on two things. We're going to plot the y-intercept, which when you plug in a 0, it should spit out A. Let's talk about what A means. Traveling back to review, yesterday's notes, A was the leading coefficient. So whatever the leading coefficient was, and when we did this, we're going to have functions that may look like something to this effect, where each position, the A position, the H position, the K position, all meant different things. Today, however, our leading coefficient is going to be concentrating on just 1. So instead of any y-intercept, today's stuff will just be 0, 1. We're going to start with plotting the y-intercept, 0, 1, and then translating it. We're going to translate it according to H and K. So the other thing was plotting the asymptote. All these exponential growth and decay models have an asymptote of y equals 0. And then again with translation. This is what we're going to practice today. That's why you have your notes. So now, those of you who are on old notes, looking at what did we do yesterday, travel to your new notes. Now we're just going to drill. We're going to practice looking at different bases and how do we transform. Not only are we looking at different bases, but our leading coefficient every single time on these notes is a 1, because you just see the base to a power. So the leading coefficient every single time is going to be 0, 1. We're going to see how that translates. So the two things we're concentrating on is how the point 0, 1 translates and how the asymptote y equals 0 translates. Looking at this graph, we've got a base of 2, but we've got this minus 4. How is this going to affect the graph? So the minus 4 is outside of the exponent. It's outside of the exponent. It's going to affect this stuff going down 4. So the old point was 0, 1. Now it's going to go down 4 to negative 3. The old y-intercept, my bad, just had a question of why is the y-intercept not 0, 2? But it's like a 1 is in front. The base is 2. So 2 is the base. The y-intercept is going to be 0, 1. So we start at 0, 1, and then we count 4 steps down. The asymptote is also going to move down 4. The old asymptote was y equals 0. Now it's going to move down 4 to be y equals negative 4. Last step is we got to recognize, are we growing or are we going to decay? And that's where the base comes involved. Our base is 2. Is 2 going to make us grow or decay? Because 2 is bigger than 1, it's going to make us grow. So we're going to be really close to this asymptote, and then we're just going to shoot up there. So again, let's practice the two things. First, we have a y-intercept of 0, 1 that'll be translated, and then we're going to talk about what about the asymptote. So this minus 3, how's it going to translate? So since the minus 3 is inside the exponent, it's going to be inversely related. We're moving right 3. So the old point, 0, 1, is moving right 3. The old asymptote, y equals 0, is moving right 3. Well, if I move that right 3, I'm still this horizontal line. Then you've got to determine, what about our base? The base is going to figure out, are we growing or are we decaying? The base here is 2 again. So because it's bigger than 1, we're going to grow again. You're close to the asymptote. You go through the old y-intercept and you grow. Here's where I'm going to be picky about shape. You see how I lift it up a little bit, like I'm not as close to my asymptote? That's bad. So I'm going to try to draw again. I'm going to try to be really close to my asymptote, and then I start growing away. We've got 2 things. How is 0, 1 going to be translated? How is the asymptote going to be translated? And then we're going to look at the base to figure out, are we growing or are we decaying? We're moving right 1, up 2. So the old point 0, 1 is now moving right 1, up 2. The old asymptote, y equals 0, now moves right 1, up 2. But moving right 1 doesn't affect it, it's really moving up 2. And determine if you're growing or decaying. Since our base is 2 again, we're going to be growing. Ooh, that was bad. Shoo! So in this next one, in general, the y-intercept is still 0, 1. The old y-intercept is still 0, 1. The old asymptote is still y equals 0. You just got to figure out, how is this minus 4 going to affect it? Hopefully in your head you're choosing down 4. So both of these items, so the old asymptote or the old y-intercept moves down 4. The old y-intercept, or no, the old asymptote moves down 4. And then look at your base. The base is going to determine if you're increasing or if you're decreasing. So since the base is 3, we're still increasing.
When would you decrease?
So now we've got 3 to the negative x. We're flipping, but it's like, do we flip the x-axis or the y-axis? You flip the x-axis if there was a negative leading coefficient. But we're going to be flipping the y-axis. This equation can actually be rewritten as, 3 to the negative 1 to the x power minus 4. We're looking at a third for our base. This is similar to y equals a third to the x power minus 4. So anytime you see a negative x in your exponent, that means our base is now transforming. Similar things still apply. The old intercept, 0, 1, the old the old asymptote, and then we'll concentrate on the base. What happens to the base? Which are we looking like? So the old y-intercept, 0, 1, now goes down 4, just like the previous one. So down 4, the the asymptote. I keep messing up on my lingo. But now because the base is a third, it's less than 1, it's going to be decreasing. So now we've got a different shape. It's going to be decreasing. We're going to be approaching the asymptote with the right arrow instead. In a similar fashion, the old y-intercept, 0, 1. The old asymptote, y equals 0. Again, we've got a minus 4 outside the exponent. So it's going to go down 4. But with the base, are we growing or are we decaying? So again, we're going to be decaying if this base is less than 1. So since we have 2/3, we're looking at something like that. Now that we've somewhat mastered graphing, now I just want you to be aware of exponential growth and decay models you're really good at deciphering, well, what am I going to do in each formula? So that's why you already have a word problem written down. You already have the models with you. And this will be the same on the test. I'm not expecting you to memorize these. Because if you were taking a statistics course, you're not expected to memorize all these formulas that are given to you. But you are expected to know what each variable stands for and how to manipulate it. So here we go. Go ahead and take a moment to read, substitute, pause. All right, so a few things. T is definitely time. Let's, I don't know, circle it, write it off to the side or something, but T means time. R is the rate as a decimal. So you're going to be given it in a percentage every single time. You got to write it as a decimal. N is the number of compoundings, so number of calculations in a year. I'm going to call it calculations. Most teachers call it compoundings, but to you it's like compounding doesn't really make sense. But number of calculations in 1 year. So how many times is this figure come back to in a year? And then the P is like your initial amount, your principal. Initial number. So in this case, our initial number is 500. Start out with 500. Our rate is 1.6%, so it's going to be 0.016. And then number of calculations in a year. So it says 1.6% annual interest compounded quarterly. So once we see this word quarterly, that means you're coming back to this amount 4 times in a year. So Rn is going to be 4. Anywhere I see an N, I'm putting in a 4. And then in the exponent, I'm going to have 4 times 3 years. We got to clean this up. So what you need to do within your calculator, we've got to figure out what that decimal is. 0.016 divided by 4. And then I also know that 4 times 3 is 12. So what I'm going to do is clean up the parentheses, clean up the exponent. And we got to relearn order of operations because sometimes we mess it up. You have to take 1.004 to the 12th power first, and then you take that amount times 500. So the accumulated amount gets us, let's see, if this is in our savings account, after 3 years we get $25. But that's if you don't touch it. Now we're going to look at decay. How can we maybe take the knowledge of the previous one and go with decay? What do you think this A stands for? And this is to anybody. Huh? Alright, so I heard annual. Well, so the bad thing is sometimes these variables have absolutely nothing to do with what they're called. The number in front of the parentheses still stands for initial amount. It's like the initial number. What are you starting out with? So initial number. Typically we deal with decay if we're calculating carbon dating in chemistry, some sort of depreciation value. R still stands for rate as a decimal. And then T, still time. All right, so if I buy a house for $210,000, that's my initial amount. That's what I started out with. You want to sell it in 5 years without improvements. So if you don't touch the house at all, find the value of the house if it depreciates at a rate of 5%, so turn it into a decimal, after 5 years. Let's clean it up. After cleaning the inside parentheses up, we've got to recognize we got to take 0.95 to the fifth power first in our calculator, and then multiply that by 210,000. What are we left with after 5 years? So we get about this amount. So if you start out with a house that's about 210,000, it depreciates over time without any improvements. And granted, I made up these amounts, but it also makes sense. If you make no improvements over 5 years, yeah, I can see that. I can see that happening. All right, so you are expected to now practice within your homework packet. I call it homework, but I really want you to work on it the last 25 minutes-ish. You know how to translate quickly. Now you know how to use models, plug things in, and so on. It's a work day, so substitute. 6th and 7th hour are allowed to work with a partner if wanted, or if they get too noisy, they have to separate. No phones. Be sure to walk around, tell them no phones until you see the first 4 pages completed. Let's go.